Hello. In this lecture, we're going to take a look at one of the earliest applications of AI in gaming, and that is for Minimax search, which is used for like turn-based games such as checkers and chess. And so there's been a lot of interest in finding ways to play those sorts of turn-based logic games. And so that's where we get the Minimax algorithm. And so let me switch over to the slides here. So we can consider the Minimax algorithm by first considering this scenario. So imagine that a parent has two children. They both want the last bit of cake that's left. And so the parent needs the cake divided for the two children. But rather than slicing the cake themselves, whether the mother or the father doing it themselves, knowing that that could lead to an argument, like the two children fighting over who has the better slice of cake, rather than doing that, the parent chooses one of the children to be the slicer. So they're given the knife, but they don't get to choose the cake. That's for the other child. So one slices and the other chooses. So this introduces a strategy that opposed strategies for these two children. So we've got the chooser's strategy and then also the cutter strategy. So the cutter knows that the sibling that's choosing is looking out for their own best interest, which is to get the biggest piece of cake. So they're aware of that. So their efforts in terms of slicing the cake is to minimize the likely outcome. And therefore, the best way to minimize the outcome for the chooser is to slice as evenly as possible. Because if they slice otherwise, slice unevenly, they know the chooser is going to pick the bigger piece. So that results in the strategy where you really try hard to slice. If you're the cutter, you try to slice the cake as exactly as possible. And then, the chooser will pick whatever one that they prefer. And then hopefully everyone is happy with that scenario. So this is what is called a zero-sum game. And you have a zero-sum game because the total amount won at the end of the game is exactly equal to the amount lost. So in the case of the cake cutting dilemma, the amount lost is whatever amount of cake goes to your opponent, and vice versa. So in that situation, you have this scenario where the two players, their interests are diametrically opposed, and whatever one player loses is gained by the other. And so there can be different versions of this, different rules that still lead to this sort of outcome. There could be a situation where you don't have any division of the winnings. Maybe it ends up being all the winnings go to one or the other. And in terms of board games, that's probably the most common sort of scenario, is where one person completely wins and the other completely loses, for instance. But you can have these sorts of splits as well, where you kind of divide like with the cake. So for this type of game, where you have the zero-sum game, there you can apply an algorithm, a general purpose solution to this, or a strategy called the Minimax theory. And so von Neumann discovered that there's this optimal strategy for each player. And that strategy is maximize their minimum potential result. So basically, what's the worst possible outcome that could arise from the various possibilities? And then try, if you have some through selection of moves in the game. If you can maximize what the worst possible outcome could be, that's the basic strategy. And so we can check out Minimax with the game of tic-tac-toe. And so in this case, it is basically a strategy of alternating. So in this case, we have a board state shown at the top. And this is at a point where the player with the X's is going next. And so they will want to pick the choice that maximizes whatever the minimum potential outcome is. And this is basically a recognition that their opponent is trying to do the same from their perspective. And so for this particular board, there are 3 slots open where the X could go. So we expand out for the next level down in this sort of tree structure we're forming. We expand out all 3 of those possible placements of the X. Now, in this situation, unless you already have some intuition about good or bad tic-tac-toe moves, we don't really know anything for either player. So we continue to expand from the perspective of each board state. So iterating through all those possible X moves as the opening move from this position. We have these 3 boards, and then at that point we have 2 slots remaining, and that is an opportunity for the player with the O's to mark their O. And so we just go through the combinations available at each point in the tree. So one or the other of the O spot or open spots to put their O. And then for the final level, you'll see that there's only one choice available for placing the X. And so that's the terminal state. So we finally gotten to a point where now we have some useful information about outcome. In fact, we know the final outcome of the board. And so we can decide who won based on the rules of tic-tac-toe. And so we see that there's some examples of a tie and X winning. So and no possibility of the O's winning, it looks like. So we can now work our way backwards to define these outcomes. Now, in this case, we have a score that we're propagating. And so we have a score of 0 for a draw and 6 for a win. And I guess presumably we could have like a -6 if the O's had won. And the score, that is something that you can, depending on your implementation, you could pick whatever scoring that you think is appropriate. But so we will propagate those values up. So there's no minimizing or maximizing values at this point because there's only the one selection there's only the one outcome. So we those values are propagated up to level 2. And so in this case, these were the results of the O's moving, placing their O. And so therefore we want to select the value that is the minimum, and because the maximum's from the perspective of the X player. So the O's would always select the value that's minimizing, staying the furthest from a win for X's. So you'll see that the 0 values, the draws, are the ones that are passed up. And so when we get to the point where X is making a solution. Well, these are all zeros here. So really, it doesn't matter which is selected. It ends up being a draw. And this demonstrates how you can get to a point where you can come up with a score. So you go to the point where you have the final outcome of the board, you propagate these values up, and then the value that gets passed up is based on whether you're at a minimizing level or maximizing level, and that just alternates according to the player. And then when you get to the very top level, that tells you whatever is the correct move to make. But there's an issue here. So with tic-tac-toe, the application of Minimax strategy, it works really easy because you can go down this tree of possibilities, and then you can go all the way to the end and find the final result tic-tac-toe board, which you can score. And so it's only those final filled boards that determine the winner, or even give us any hint as to how well a board is looking. But what if we tried to work with something like chess instead? Well, chess, we've got a problem because the range of moves that to be considered, to even go just slightly deep into possibilities, will easily run out of time and memory to evaluate all of the possibilities. So there's no way we can search to a final board state. There's also some other problems with chess in that you're not necessarily always moving closer and closer to a result. You can actually have what are basically infinite loops of pieces just moving in circles around the board. So this creates a challenge to apply the Minimax strategy. So how might we deal with this problem? So for any game such as chess, where you are just unable to go exhaustively evaluate all the way until the end, you instead, a common approach is to create an evaluation function. So this is like a heuristic that we will apply to evaluating an entire board state or game state. And it will give us a score that we think generally shows whether the current state favors one player or the other. So once you have the ability to score a board or a game state, then that allows an evaluation to a partial depth. So not to completion, but just some number of player choices or moves. And so you go to some max depth that you've determined, or maybe you're measuring to see like some amount of time. So it depends on the game. Like in chess, you might have a time limit, real world time, and so the computer would need to be aware of that, or that'd be part of the strategy. Or it's just reasonable not to take millions of years to solve. So you might say, well, we'll go to say a depth of 5, because you just empirically you determine that takes the computer maybe 10 seconds, and that your players are going to get bored if they have to wait more than 10 seconds for a move to be made. So you evaluate to the point where you have a leaf, or the terminal depth that you are reaching, and then you score the board with this heuristic. And so the heuristics are really going to vary depending on the game. How you go about doing calculating this, could be based on the ratio of playing pieces, like which side, player A or player B, has more pieces. It might be who's gotten closer their playing piece to some destination. It could be some sort of weighted average by the types of pieces you have. But you have to be careful though. You don't want so it's kind of similar to the heuristic in path planning that when we were on the topic of path planning, you don't want to have a heuristic that is too expensive to evaluate, because then it detracts from being able to more thoroughly perform your searching. And so same with Minimax, you want to be able to efficiently explore. So really it's a balance of not having a heuristic that is so expensive that it holds you back. All right. So in the case of chess, there, if there was a perfect evaluation function, then you wouldn't even need to be performing the search. But there are some reasonable sorts of strategies that you can use for creating your evaluation function, the scoring the state of the board. So some of the criteria you might have are is the opponent's king in a checkmate, and so that is the normal winning condition, and so you certainly want to make sure that your scoring captures that if it's a terminal state, and so then probably you'd want your score to be infinity, it favoring either one side or the other. So positive and negative infinity. We'll use positive and negatives for like white and black team players. Then you could also look at which player has more pieces, and so you could have a score contribution related to that. And then maybe the queen is such a valuable piece that you might have some comparison to see if one player has the queen but the other doesn't. So you have a scoring that way. You could also have pieces with relative values. And so of the remaining pieces, we could sum according to these weights, such as shown on this slide. So a pawn is not worth much, but a king and a queen are worth a lot. And then the other pieces are worth appropriate amounts. And then maybe there would be some certain relative positions as well, maybe specific to certain unit types. There could be some value there. But again, you have to be careful in how much you add to your scoring function. But you ultimately can get a score, and then that once you have a score that's reasonable, that facilitates the propagation back up from the leaves, and then the alternating, maximizing, minimizing up to the root. And that informs the agent, which is the most appropriate move to take of the available moves. So there are improvements we can make to the Minimax algorithm. We can, for instance, identify states where we shouldn't explore any further. And so some of these are pretty straightforward, such as if the agent has lost, then you don't need to further expand moves. You terminate there. So you might have a leaf that appears in your tree of possibilities before the maximum depth is reached. Also, you might recognize that there is a loop, like a repeating pattern. And so in those cases, if you've detected the loop, then you can just terminate at that point, further expanding that node or that line of nodes or branch of nodes. Another powerful technique is called alpha beta pruning. And so this is where you're tracking the best moves. So this is based on the Minimax algorithm, actually the propagation back and the scoring. And so you can consider as you go like down to the maximum depth and then propagate back up, you can go ahead and make those scoring decisions. And then so you know what the best score you've seen so far is. And you can carry that data along with you, or reference that data as you propagate down other branches. And so if you find a branch that, if you expand it, leads to something that's guaranteed to not score better, then you prune the branch. You don't need to go any further. So so that is a good way to improve on the Minimax, because that allows you to spend more time expanding nodes that have the potential to be a good solution without wasting the memory and computational time. Some other approaches include iterative deepening. So you go to a reasonable depth first. And this would be based on like the time allowed. Pruning might allow for further search, or for whatever reason, you might decide that you want to go deeper. Also, this can play in nicely with games where you have, let's say, an overall allocation of time, like an hour. So you might first try to see if you find a move you're happy with a small depth, and then if you're not happy with it, then you might decide, well, I really need to exert more effort searching deeper. So maybe you go past your average desired time allocation, but it's worth it because you're in sort of a sticky situation, or your agent is. In terms of trying to like optimize Minimax, another thing to do, rather than like allocate memory as needed as you're expanding the tree, instead just pre-allocate an entire tree structure. So everything's just ready to go. There's no like memory allocations or recursive calls or anything like that. You just are filling out a pre-existing structure. And so this is a popular approach to use. You can also employ case-based reasoning. Case-based reasoning fits in nicely with the Minimax strategy. So your cases end up being like board states that have been seen before. And you can also cache outcomes of the search, like what was the previously calculated evaluation score, what was the best of those moves. And these can reflect a history of previous matches played by the agent, and can also even include historical matches, even like human versus human, which is quite common and has been used in many of the chess agents in terms of their solving, leveraging a case-based reasoning knowledge base. Yeah, so there's lots of improvements that can be made to Minimax, and often need to be employed, especially when you have these games with lots of possibilities. Now, there is a situation where we might have games that have more than just the two players. And so we could consider ways that maybe we could extend the Minimax algorithm to work for N players. And so in this case, you could just alternate the selection for each player as part of the min and max. You now just have these additional steps for each player, other than the agent that you're like say the Minimax algorithm from the perspective of the agent that you're writing the code for, then you'd have each other player's choices being made as a part of the algorithm. So just incrementally stepping through according to the rules of the game, like player A, player B, C, D, E, and then recycle or restart with A again. But the a problem with this approach is that in some games, players may work together. They may collude and work against you or work against your agent that you're writing the code for. And so there's actually, this is kind of a common problem for board games, especially with more than two players. And so, in fact, it's got a name when say one player, like say you're playing a game and you're doing well, then everyone decides because you're doing well to gang up on you, and then knock you down. And this can create sort of a vicious cycle, and it has implications on applying the Minimax theory. And another problem is that human players will often participate in what's called king making. And so this is where, let's say, a player it has basically been mathematically eliminated. They know they cannot win, but they're not removed from the game. They're still a participant. They just can't win, or highly, highly unlikely that they could win. But they still have some agency in the game, in that they can take actions that impact the outcome. And that is, they could pick someone that has a chance and give them a boost. And so this could be for just arbitrary reasons. They don't like you or whatever. And so that this whole king making thing. And so between the possibility of players ganging up on whoever's doing the best, or this king making, or other types of collaboration, that can cause a situation where the Minimax algorithm is not effective. And so a strategy to deal with this is to actually redefine the game, to have a new perspective, and that is where you consider it you or your agent versus everyone else. So you effectively make the game two-player, but you've got this more complicated simulation now where the second player has these multiple stages where they're picking their best outcome for how many ever players there are in addition to your agent. And so other than coming up with this slightly more complicated alternation between the min and the max step, or the expanded step for the aggregate second player, you otherwise use Minimax as normal. The downside to this is it can result in overly cautious game decisions, and another thing, an observation, that some of these games are actually not zero-sum games. They can have non-zero-sum possibilities, and that are games where the outcome maybe varies, or the amount that can be won or lost can change based on game time decisions. So maybe a game actually supports or promotes a collaboration, and those that collaborate win even more than if they had just tried to act alone. So you really have to be cautious, and if you're going to try to write like a Minimax style algorithm, make sure that it's truly a zero-sum game. So what about other types of zero-sum games, such as ones that are probabilistic? So this is an interesting challenge to face, and so this it will typically involve games that include rolling of dice or shuffling a deck of cards and allocating the cards um, to different players, and so you don't always start from some well-defined state, um, and so games like Settlers of Catan, for instance, would be a good example. And so there's a variation of Minimax called Expect a Minimax. And so this is just a variant where we introduce, as part of the minimizing and maximizing steps, we have chance nodes that are interleaved between the min and the max nodes. And so you might, and it's going to depend on the game's rules how exactly this tree structure is going to be formed, because you might have the chance nodes between each player, or one chance node and then both players go. And so again, it's going to depend on the game how this is applied. But the main thing is just to be aware at these points at which you have these chance possibilities, you introduce these additional nodes into the tree structure. And so a chance node, as you are passing or propagating back up the values from the leaves, you are taking a weighted average of the children, with the weight being the probability that the child is chosen randomly. So you basically, the chance is leading to the possibility of each of these moves being considered. But otherwise, you again are evaluating the min and max the same as you normally would. So here is an example of expected min and max, and so we say go all the way to this bottom depth where we have our evaluation function applied, or perhaps this could also be a game with a terminal step, but generally that's not the case where you actually can evaluate to a final step. So we have these evaluations, and so like in the bottom left here, those two siblings, we have a 6 and a 2, and so each branch, based on the chance outcome, say like flipping of a coin, perhaps there's a 50% chance of leading to the left child, and 50% with the right. Now the scoring of the left child is a 6, or the valuation function gives a 6. And then the right gives a 2. But there's a 50-50 chance that you'd lead to either one. And so we take a weighted average, and at that level, those two branches are 50% each. So that would be 6 times 50% and 2 times 50%, or 6 divided by 2 and 2 divided by 2. So that would be 3 plus 1 is 4. And so at that chance node, we have a 4. And so you can see similarly, we have other chance nodes that are populated. And then at this point, based on the min and max alternation, for this example, we would be choosing the minimum. So we have a 4 and a 2, but we would be minimizing. So we pick the 2. So that would be the branch to the right. Then that goes up, and then so we have another opportunity to do our weighted average to pass values up to the next chance node. And so again, you just multiply out according to the weights. And these could be different, if you're rolling 1 die versus 2 dice. Maybe you have some other type of rules involved. So you would have different chance possibilities. Maybe it could be based on like drawing cards and so on. It can get a little complicated to figure out exactly how to build the tree, but once you get that sorted out, it's just a weighted average and propagating up the values, and then the min and the max as normal. So there are other ways that you can go about building an AI for the sort of zero sum turn based games. And one strategy that is useful is the Monte Carlo tree search. And so this uses a much different technique, though if you evaluate it far enough, it ends up being essentially the same as the Minimax strategy. So the basic idea is perform an analysis of the most promising moves, expanding the search tree based on random sampling rather than just meticulously expanding all possibilities. So you start off with a particular board state, you don't know anything, and then you just start picking randomly. But then as you pick randomly, that starts to inform you, and you start to know, well, which moves are promising from the perspective of one player or the other. And so you expand, and then do this random sort of searching through the possibilities, and then that continues to update these sort of running statistics of the moves, and you keep doing this until you like run out of time to go any further. So it's kind of similar situation to the Minimax. You're assuming that you can't really expand any further, or you possibly also could run out of memory. But in either case, at that point, you just return whatever the best result you've got so far. And again, you're always tracking what are the best moves you've found. And so this is popular for games that have like a really high branching factor. So as you're building the tree, if the tree gets bushy really fast, then it's really hard to figure out a way to explore to any great depth. But with the Monte Carlo tree search, you do have this potential to search all the way until a terminal state for informing your selections. So in a little more detail, we've got these four key steps to performing the Monte Carlo tree search. So you start with selection. So you start with a root node that represents the current board state, and you select a successive child node down to a leaf node L. So this figure here, this is considering that the Monte Carlo tree search has already been applied a few times. So we've already built out some bookkeeping of promising nodes. So of the nodes that you already have this bookkeeping for, those are the ones that you expand down until you get to the point of there being a leaf. Now the leaf that you've got is just the leaf so far, and it is not going to usually be a terminal state. It's just going to be at some arbitrary depth of moves considered. So then when you're at a leaf, you're in this expansion state. And so again, assuming this is not a win or loss for the player, then what you do is you create a new child node, and then choose to expand that node. So you play out a random play out from that node, and this random play out it's not informed in any way. This doesn't mean do Minimax or use a heuristic or anything. In fact, it would probably work against you to use a heuristic, because then you would introduce some bias, and the random simulation would not give you a good coverage. So you actually just literally want the play out part or the simulation part to just pick from valid moves, but have equal possibility for any move as you expand. And so that could be some arbitrary number of moves for like the player A and player B if it's a 2-player game. You just keep going down. Again, no bias of any sort, and you go all the way until you finally get to a conclusion where one player or the other wins. At that point, you perform back propagation. Now, you've expanded all those nodes. It could be quite deep in terms of expansion, but those do not form nodes that you preserve. That you throw away all of that information, and all you care about is what the result was. And so that is a data point that brand new node C that was created is updated to include the outcome. And then after that, you update all of the scoring or the bookkeeping along the path that led to that node from the root node. And then once you've updated all those stats, then you can restart again from the selection phase. And then when you're selecting, you're again picking the most promising node for each player, and then you work your way down to a leaf again, and then you perform expansion again, and so the bookkeeping stats are going to keep updating over time, and so you might eventually realize that what was originally a promising branch will start to pick up on some poor examples, and maybe it gets overtaken by another path through the tree that's being built, and so then that new path starts to be expanded upon, and the leaves visited and simulations run on that side. So this search tends to favor the most the most promising nodes. So here is an example of this. So the scoring that's shown here, whether we have the white circle or the gray for black, this is showing the denominator is the number of games played from the perspective of that node. So it'll always be the sum of the whatever children nodes are underneath, the sum of those denominators. And then the numerator is going to be from the perspective of whichever player the color is shown. So for instance, for the root node, the white node, that is with the white player making a selection. That's what the Monte Carlo tree search is trying to solve for in this case. So we have 11 out of 21 so far, and then you can consider these different nodes, and again these nodes that are shown here. This is like midway through the running of the Monte Carlo tree search, and so the next level down we see like the 7 out of 10, 3 out of 8. And so that's the perspective of the black game piece. So that player has looks like a favorable branch on the left. So that would be the branch selected for the black team. And then the white for white we pick the minimizing, sort of same as the Minimax algorithm. So you're maximizing and minimizing, minimizing as you go down, expanding. So you start with 11 out of 21, the root node. There's no choice at that node, but at the children you pick maximizing for black, and then minimizing of those choices under the 7 out of 10, the minimizing, and then you choose maximizing again. Now at this point, so you'll see you end up at the 3 out of 3. And so that's where we will need to create a new node. And so this new node has no stats yet. We just have 0 over 0 for now. So we need to run a simulation or a play out. And so we run, again, just randomly selecting, no heuristic or any sort of bias in the selections. All we need are just valid choices, following the rules of the game. So that results in, let's say, a loss for white. And so at that new node that was just created, we would update the count on the denominator and then then have a 0. And so we store those two values separately. And then it can also, and then actually running the division gives us our score. And so we can propagate all the bookkeeping upwards, which will update the denominator for all nodes, propagating up to the root node. So the 3 out of 3 now becomes a 4 out of 4. The 1 out of 6 becomes a 1 out of 7, and so on until you get to the very top, and you have all those stats updated. And then you run it again and again and again and go until you've run out of time or memory or whatever your allocation is. And then you pick the move that is most appropriate. So how can we improve on the Monte Carlo tree search? So we want to continue to refine these estimates of the quality of the moves, but we also want to make sure that we're exploring these new paths through the tree. And that's because we might uncover some promising move, whether it is something we can force our opponent down a particular path, or maybe our opponent has like a move that they would be likely to select. And so we want to make sure that we find that, or as many as possible, the moves that our opponent would be likely to select. So how can we do this? How can we refine the moves? Pardon the interruption. This video has been modified to remove a redundant discussion of exploration and exploitation, which is already covered in the learning module under the title Exploration and Exploitation. This particular lecture does have a prerequisite of being familiar with that material, so if you haven't seen it yet, please check it out before continuing. So we can think about the steps of the Monte Carlo tree search and how we might come up with a variation on the selection step that's leveraging this notion of exploration and exploitation. And the idea is we want to avoid getting stuck on any like local maxima minima type of situation. And so we're going to have this little augmentation in terms of making our selection for which move to expand upon. And so we've got this equation here where we're going to consider the wins for the node. This would be after like the nth move. So all of the subscripts with the I, that just means after you've made the ith move. So we've got our wins and the number of simulations run. And so So that's that looks like kind of standard to what we were talking about before. So for a particular color, the wins over the number of um, runs that we've had, the rollouts that we've performed. But we're going to add to it this additional term. And so by the way, the wins over the total number of simulations so far, that's like our exploitation term. That's our stat that tells us, that the ratio that we think is accurate. But while our n is small, we have this decaying exploration term. So if our n is small, that means that our w over n is not necessarily very accurate. We could have had an early success, but that's not something that's going to stick long term. Alternatively, we would have maybe the exploitation term scored very low just from some unlucky situation, and so we can boost those with this exploration term. So we have this natural log of n, and that being the total simulations for the entire tree, not just following through that particular branch. So in terms of going through a branch, the lowercase n is that number, but the uppercase n reflects the total number of simulations. So take natural log of that divided by n, so that the local simulations of the branch, square root of that, and then multiply times c, which is this exploration parameter to kind of be able to tweak things. Theoretically, that should be a square root of 2, but in practice, it's tuned or selected empirically. So when you take the summation, that exploration term can be a significant boost to the w over n value, and so that's going to result in a more likelihood of certain nodes being expanded upon, and then adding the additional nodes as part of the Monte Carlo tree search, and then also performing the rollouts from along that branch. But over time, that the decaying exploration term will start to go towards 0. And now our scoring will be dominated by just the w over n. And so this has some nice properties because it improves on this ability to balance the exploitation and exploration. So in terms of just Monte Carlo tree search in general, not with UCT, but in general, it will converge slowly towards Minimax equivalency, but it by nature, you've got this incomplete coverage of the search space. So it tends to be kind of like taking these long depth-like samplings of possibilities. And that means that because of that approach, that means that some negative possibilities will be missed, even at a short depth in the tree. Like you could miss something that, say, 3 or 4 moves in, if you don't go long enough with the Monte Carlo tree search, would be like very obvious. Maybe even just really poor choice compared to what a human would just immediately recognize. But with UCT and other similar sorts of variants, you can help reduce these sorts of possibilities with balancing the exploration. But advantages is that it does eventually converge to Minimax. It minimizes the search space. with advantages in doing so, this minimizing as compared to like a Minimax with an alpha beta pruning. And you don't need an evaluation function other than just recognizing the final board outcome, because you are going all the way to the end and knowing the winner for the random play out. So that has nice features, because it can be really tricky in some games to come up with an evaluation function that is useful for combined with the Minimax. But you could potentially perform an incomplete. With the Minimax, you need the evaluation function, because you're not going to be able to explore as far as a Monte Carlo tree search. So that's the advantage of especially Monte Carlo tree search in comparison to Minimax, and it's easily applied also to probabilistic zero sum games as well. So you can similar to expect a Minimax, you can have the same sort of strategy. So both approaches are popular, either Monte Carlo tree search or Minimax, and there's various ways that you can improve them. And so in terms of picking one or the other, it's really going to probably depend on the game. Some games will lend themselves more to one or the other. Like I mentioned before, some games that have this high branching factor of the possible moves tend to fit better with a Monte Carlo tree search. But yeah, both are effective and are good ways to build like board games or turn-based games. So all right, we'll stop here, and if you have any questions, feel free to reach out.